Welcome to this explainer. Right now, down in southern India, specifically in Kalpakkam, there's a revolutionary 500 megawatt breakthrough happening. It literally sounds like pure science fiction, but it's a technological marvel that's completely reshaping how we understand energy. I want you to consider this paradox for a second. What if a reactor actually produced more fuel than it consumed? We are so used to this use it and lose it concept of burning resources, right? You burn coal, it turns to ash. You use gas, well, it's gone. But imagine a machine that completely defies this rule. A machine that literally creates more usable fuel just by running. To really grasp why this is absolutely crucial, we have to talk about the stakes here. Look at this number, 85%. That represents India's current reliance on imported oil. Think about that. Every liter of petrol, every tank of cooking gas, a massive chunk of it has to be shipped through vulnerable global choke points. So, for a rapidly growing nation of 1.4 billion people, this staggering reliance highlights an absolutely urgent need for total energy independence. Okay, so let's look at today's agenda to see how they plan to do this. We'll start with a fire that breeds fuel, then cover the signs of fast breeders, the three-stage master plan, India's thorium endgame, turning waste into wealth, and finally, wrap up with the global picture. Section 1, a fire that breeds fuel. So, our story centers on a really historic, recent event in the coastal town of Kalpakkam in Tamil Nadu. This is where India essentially lit a very special kind of fire inside their Prototype Fast Breeder Reactor, achieving a major milestone. What they achieved is called criticality. Now, I know the word criticality sounds like some huge alarm bell in a sci-fi movie, but in nuclear terms, it actually represents perfect balance in safety. It's just the precise point when a reactor achieves a self-sustaining chain reaction without any external help. The neutrons produced perfectly equal the neutrons lost. Not too much, not too little, just perfectly, wonderfully balanced. Actually, there's a brilliant analogy for this. Think of a spinning top. When you first spin it, it kind of wobbles, right? But criticality is that beautiful moment where it finds its perfect self-sustaining axis and just keeps spinning entirely on its own. You step away, and it just goes. The Kalpakkam reactor basically just found its permanent axis. Section 2, the science of fast breeders. Let's dive right into the rapid-fire physics of how exactly this machine pulls off creating more fuel than it uses. So, conventional reactors use water as a coolant. The thing is, water slows down the atomic particles. It's very much a use-it-and-lose-it system, almost like burning coal. Breeder reactors, on the other hand, use liquid metals, like liquid sodium or lead. Why? Because liquid metal doesn't slow down the split atoms. It ensures those neutrons remain super fast. And keeping them fast is the whole secret here. Here is how the magic happens, step by step. Inside the core, fission creates extreme heat and fast neutrons. Wrapped around that core is a blanket of non-fissile uranium-238, which normally can't sustain a reaction on its own. But when those super fast neutrons slam into that blanket, the uranium-238 absorbs them and actually transforms into usable plutonium-239 fuel. It is literally breeding its own replacement fuel while it generates electricity. How wild is that? India's nuclear establishment describes this with such a wonderfully poetic phrase. They call it an Akshaya Patra of energy. If you're not familiar, in Hindu mythology, the Akshaya Patra is a divine vessel that simply never empties. No matter how much food or resources you take out of it, it just keeps filling itself right back up. Section 3, the three-stage master plan. Now, this breakthrough definitely wasn't an overnight discovery. We have to zoom way back to the 1950s to talk about the visionary architect behind all this, Dr. Homi J. Bhabha. Dr. Bhabha actually did the math on India's energy future back in the 50s, mapping out this staggering 70-year relay race. Fast forward a bit to 1985, and the Fast Breeder Test Reactor begins operation just to test the tech. By 2004, over 200 Indian companies started constructing the massive Prototype Fast Breeder Reactor. And finally, on April 6, that exact reactor achieved criticality. We're talking about generations of scientists passing the baton to reach this specific moment. And here is how it all fits into Bhabha's famous three-stage plan. Stage 1 relies on heavy water reactors burning natural uranium, which creates plutonium as a byproduct. Then we get to Stage 2, which Kalpakkam just officially unlocked. This stage takes that plutonium, puts it in a fast breeder to make even more of it, and, this is the critical part, begins converting a completely different element, thorium, into uranium-233.
Which brings us to stage 3, the ultimate destination, advanced reactors running entirely on that thorium-derived U-233.
Section 4, India's thorium endgame. So you might be wondering, why thorium? Why go through the trouble of building this incredibly complex three-stage system? Why not just do what the rest of the world does? Well, the answer comes completely down to geology. India has pretty modest uranium reserves, but it happens to sit on roughly 25% of the entire world's thorium. We're talking nearly 500,000 tons just sitting on the beaches of Kerala, Tamil Nadu, and Odisha. That massive, unmatched stockpile is the entire justification for this whole program. But of course, there's a catch. Thorium is what we call fertile, not fissile. That means you can't just throw it into a reactor and expect a chain reaction. It just doesn't work alone. It absolutely has to be placed in the blanket of a fast breeder reactor to convert into usable nuclear fuel, specifically that uranium-233. So mastering the breeder reactor was the one and only key to unlocking this massive thorium battery that literally has enough supply to power India for centuries.
Section 5, turning waste into wealth. Okay, let's explore one of the absolute coolest benefits of this closed nuclear fuel cycle and how India takes what the rest of the world calls waste and turns it into absolute wealth.
I love this analogy. It's exactly like squeezing sugarcane. In stage 1, you take the full sugarcane and squeeze out that initial juice. But instead of just throwing the crushed cane away as waste, stage 2 takes that exact same crushed cane and squeezes it again inside the fast breeder. And then stage 3, it squeezes it a final time. They literally throw absolutely nothing away. The environmental impact here is a real game changer. Without reprocessing, conventional nuclear waste stays dangerously toxic for tens of thousands of years. It's a huge headache. But with India's specific reprocessing method, they extract the actinides and reuse the fuel. The actual leftover waste volume shrinks down to just 2 to 5%, and its toxicity drops to roughly 300 years. It completely solves that dreaded long-term nuclear waste problem. And here's a really surprising bonus fact for you. These fast breeder reactors run extremely hot because of the liquid sodium, producing steam at 480 degrees Celsius. You can actually divert that intense heat to power high-temperature electrolysis, which creates greener-than-green hydrogen. It's just this massive, carbon-free add-on to an already revolutionary system. Section 6, the global picture and future. So let's bring this explainer into the present day and see how India actually stacks up against global superpowers in this space. When you look at functional, commercial-scale fast breeder reactors, there are literally only 2 nations on Earth that have cracked it: Russia and now India. China currently only has a test reactor. The USA and France, well, they both tried it decades ago, hit a bunch of technological snags and massive costs, and ultimately abandoned their programs. But India persevered, and now they're sitting in a very exclusive 2-nation club. And they are scaling up fast. Look at this growth target. In 2024, nuclear power is just a small fraction of India's energy mix, sitting at about 8,180 megawatts. But to meet the crazy demands of a rapidly developing economy, they're targeting 100 gigawatts by 2047. That is a historic, unprecedented leap. Which leaves us with this really profound thought. For 70 years, a relay race of scientists has been tirelessly building a machine to secure their future. And now that they have finally lit a fire that breeds its own fuel, you have to ask yourself, if a nation of 1.4 billion people actually achieves total low-carbon energy independence for centuries, how does that reshape the geopolitics, the economy, and the future of the entire world? Thank you so much for watching this explainer, and I'll catch you next time.